Imagine standing near a massive industrial furnace in the late 19th century. The heat is stifling, and the air is thick with the smell of burning coal and hot grease. You are watching a machine consume mountains of fuel just to move a single heavy piston. And as you watch, you realize that most of that energy is simply vanishing. It is escaping into the air as wasted heat, drifting away in the smoke and vibrating uselessly into the floor. In the 1880s and 90s, this was the sound and smell of progress, but it was also a sign of a massive, hidden failure.
The world at that time ran almost entirely on steam. Steam engines were the giants of the era, powering the massive ships that crossed the oceans, the locomotives that knit continents together, and the factories that produced everything from textiles to steel. But these engines were incredibly inefficient. They were hungry, clunky beasts that required massive boilers, huge piles of coal, and a constant army of workers just to keep them fed. A typical steam engine of the day was lucky to convert even 10% of the energy in its fuel into actual movement. The other 90% was lost. This was the hard constraint of the 19th century. We were burning the world to move just a little bit of it. Engineers and thinkers knew there had to be a better way to get more work out of every pound of fuel. They were hitting a wall where simply making a steam engine bigger did not make it better. A bigger engine just required a bigger boiler and more coal, which meant the ship or the train had to be even larger just to carry its own fuel. It was a cycle of diminishing returns. The dream was to find a way to make the fire happen exactly where the work was being done, cutting out the middleman of the boiler and the pipes full of scalding water. This led to the early experiments with internal combustion. Some people were already playing with light fuels like gasoline, but those early engines were finicky and often dangerous. They relied on a spark to start a fire, and that fire was hard to control. The real breakthrough came from looking at the pure physics of how air behaves when you squeeze it. This is the scaling trick that changed the history of transportation. If you take a volume of air and compress it into a tiny space very quickly, it gets hot. It does not just get warm, it gets hot enough to set things on fire instantly. The key insight was that if you could compress air until it was white hot, and then spray fuel into it at exactly the right moment, the fuel would ignite on its own. You would not need a spark plug or a delicate electrical system. By 1897, after years of experiments that resulted in several massive explosions and at least one near-fatal accident, a working prototype proved this concept was viable. This new kind of engine did not just run, it ran with a level of efficiency that was twice as high as the best steam engines in the world. This changed the math of global trade overnight. If your engine is twice as efficient, you only have to buy half as much fuel. For a ship owner, that meant the space once filled with thousands of tons of coal could now be filled with profitable cargo. But getting this technology to scale up was a monumental task. You could not build these engines in a standard blacksmith shop. They required a level of precision that was at the absolute edge of what the technology of the time could handle. The cylinders had to be perfectly round, and the fuel injectors had to be able to spray a fine mist of oil into a chamber that was already under immense pressure. This demand for precision pushed the entire manufacturing sector forward. It forced the development of better metal alloys that could withstand extreme heat and pressure without cracking. As these engines began to grow in size, they started to take over the roles that steam had held for a century. The first big win was in the shipping industry. Before this, a ship was basically a floating coal bin. It had to stop at ports all over the world just to refuel, creating a massive global network of coal stations. But with this new high-compression engine, ships could carry liquid fuel in their double bottoms, freeing up the entire hull for goods. The spread of this technology created an entirely new system of logistics. We needed a global network of oil stations to replace the old coal docks. We needed a new generation of engineers who understood high-pressure thermodynamics rather than just how to keep a fire burning. It also changed the military landscape. Suddenly, submarines became a viable weapon because they could use these efficient engines to travel long distances on the surface and then switch to electric power when they went underwater. The ripple effects were felt in every port and every industrial city on the planet. One of the most fascinating parts of this story is how it changed our relationship with fuel itself. We went from burning messy, solid coal to using liquid oil that could be pumped through hoses. This was cleaner, faster, and required far fewer people. The human scale impact was huge. The stokers who lived in the hellish heat of the boiler rooms, shoveling coal for 12 hours a day, were slowly replaced by technicians who monitored dials and maintained high-pressure pumps. The sheer physical labor of moving the world began to subside, replaced by the mechanical efficiency of high-compression combustion. As we moved into the 1920s, the technology started to scale down as well. It was no longer just for giant ships and power plants. It found its way into trucks and tractors. This revolutionized farming. A tractor with an efficient engine could do the work of dozens of horses without needing to be fed when it was not working. This led to a massive increase in food production and helped drive a migration of people from farms into the growing cities. The efficiency of the engine was a hidden driver of social change, making it possible to feed and move more people than ever before. Today, we are so used to the roar of these engines that we barely notice them, but they remain the heart of our world. Almost every single thing you own, from the food in your refrigerator to the clothes on your back, likely spent time on a ship, a train, or a truck, powered by a descendant of those early high-compression engines. Even with all our modern technology, we still struggle to find anything that matches the combination of power, reliability, and efficiency that these machines provide for moving massive loads over thousands of miles. The environmental cost of this success is a conversation we are having now, but the logistical capability of these machines is what created the modern globalized economy. The journey of this engine shows us that sometimes the biggest revolutions are not about the flashiest inventions. They are about finding a way to do more with less. It was the scaling trick of squeezing air to create heat that allowed us to build the modern world. It was a leap in the math of what was possible, and it set a standard for efficiency that has lasted for over 100 years. We are still riding on the back of a breakthrough that happened in a small laboratory over a century ago, a breakthrough that proved that how you use your energy is just as important as how much of it you have. As the world was being knit together by these powerful and efficient engines, another technology was quietly evolving alongside them. Engineers were beginning to realize that while liquid fuels were great for long distances, there was another way to store and use energy that did not involve combustion at all. In the late 1890s, as the high-compression engine was proving its worth, the race to master chemical energy storage was just beginning to heat up. In the next episode, we will move forward to 1899 and look at the early days of batteries before lithium was ever on the horizon. We will see how lead acid and nickel chemistries attempted to power the future, and how those early lessons still shape our world today. If you enjoyed this look at the history of technology, subscribe to follow the rest of the series.